Chapter 6, Section 3, Linear Independence. In data science, the concept of linear independence indicates whether features or vectors contribute unique information or overlap with others. In the previous section, we learned the concept of matrix rank. In this section, we will see how we can use the rank of a matrix to identify linear independence. By completing this section, you can understand how rank and linear independence are related and how they are applied to real-world problems in data science. Before diving into the concept of linear independence, let's check our understanding of the foundational concepts, independence and redundant. Independence has various meanings, but in data science, it often refers to the property of features or variables being unrelated or uncorrelated. When variables are independent, knowing the value of one variable does not provide information about the other variables. The term independence in linear independence refers to this meaning. On the other hand, redundant refers to features, variables, or data points that do not add unique information because they are strongly correlated or dependent on others. Redundancy can lead to inefficiencies in analysis and modeling. For example, if two variables are highly correlated, we can often remove one of them without losing meaningful insights. A set of vectors is said to be linearly independent if no vector in the set can be written as a linear combination of the others. In other words, none of the vectors is redundant or dependent on the others. If at least one vector in the set can be expressed as a linear combination of the others, the vectors are linearly dependent. Consider a set of vectors v1, v2, vn in Rm. These vectors are linearly independent if the only solution to the equation c1 v1 plus c2 v2 plus cn vn equals 0 is c1 equals c2 equals cn equals 0, where 0 is the zero vector. If there exists a non-trivial solution, that is, not all coefficients are 0, the vectors are linearly dependent. As an example, let's consider the vectors v1 and v2 in R2. To check if they are linearly independent, we need to see if there are scalars c1 and c2 such that c1 v1 plus c2 v2 equals 0. And both c1 and c2 are not 0. This equation can be written in this way. Breaking this into component equations, we get the following. Here, the second equation is simply twice the first, indicating these vectors are linearly dependent. A solution is c1 equals 2 and c2 equals minus 1. So the solution is non-trivial. So v1 and v2 are not linearly independent. Now consider another vectors v1 and v2 in R2. For these vectors, the following equations hold. This results in c1 equals 0 and c2 equals 0. Since the only solution is the trivial one, v1 and v2 are linearly independent. The rank of a matrix is closely related to the concept of linear independence. The rank of a matrix is the maximum number of linearly independent rows or columns it contains. Thus, determining the rank of a matrix involves checking for linear independence among its rows or columns. Let's recap the two concepts that we learned in the previous section, full rank and reduced rank. If a matrix has full rank, It means all its rows are linearly independent. If a matrix does not have full rank, some of its rows are linearly dependent. As an example, let's consider this matrix A. To find a rank, let's perform row reduction. First, subtract 4 times the first row from the second row. Next, subtract 7 times the first row from the third row. Then, divide the second row by -3. And then, add 6 times the second row to the third row. The resulting matrix is in row echelon form, and it shows 2 non-zero rows, indicating that the rank of matrix A is 2. This means there are 2 linearly independent rows or columns in matrix A. The third row is a linear combination of the first 2 rows, confirming linear dependence. Linear independence is useful in machine learning for identifying and removing redundant features. It is meaningful because by eliminating redundant features, we can prevent overfitting of a machine learning model. Removing redundant features enables a model to be generalized better to new data. Moreover, a simpler model with fewer features is easier to understand and explain, which is especially important in domains where transparency is key, such as healthcare, finance, and human resource management. Furthermore, linear dependence among features can lead to numerical issues such as multicollinearity, which affects the reliability of coefficient estimates in models like linear regression. In the following chapters, I will explore this problem in more detail. Let's summarize what we have explored in this section. Linear independence is an important concept in that it is useful to determine whether vectors or features provide unique information. We can use the rank of a matrix to identify linear independence. By ensuring linear independence, we can simplify models, prevent overfitting, and enhance their interpretability. These are critical to build effective and efficient models. Thank you for watching. Please thumbs up and subscribe to my channel.